is something that you need to consider, and I'll try to explain to you how to do it. With that, let's dive into the detail because we need to keep up the pace now. So why do we need to do it? Why large data sets? Why large neural networks? Yes. And it's an important question to ask, especially since we continue to see a bigger neural network across every single discipline and every single artificial intelligence field almost every day. Yes. And that growth seems to be very consistent. And not only it's not slowing down, but it seems to be accelerating, especially over the last 2 years. We've seen a fairly dramatic acceleration in the size of the models that are being used. In natural language processing, yes, but also in quite a few other disciplines. And being able to understand why do those neural networks grow is critical to understanding of how to improve overall performance of artificial intelligence algorithms. So the reason why they are growing is actually quite straightforward. For reasons that are not yet fully understood, larger models trained on larger data sets behave better. And they don't just behave better in an arbitrary way. Irrespectively of what problem you're trying to solve, there seems to be a fairly fixed relationship between especially the amount of data that you have for training and the performance of your model. So this is one of the earliest studies that I know of that is looking into this relationship. It was presented, I think, on NIPS in 2017, so December 2017. And it looks at this particular study, 5 different problems: translation, language modeling, character language modeling, image classification, and attention speech modeling. And what they've done in the studies, they have trained a number of different neural networks, which are representative for the problem that is being solved, with different amounts of data. They started in this case with 2 to the power of 20 samples. They've trained the neural network, evaluated its performance. They've trained it with 2 to the power of 21 data samples. They've evaluated its performance to generate the curves that you're seeing in front of you. And the immediate conclusion that they came up with is, as the title suggests, deep learning scaling seems to be predictable, at least empirically. So there seems to be this underlying relationship between the total amount of data that we have and how well our model behaves. And they concluded by suggesting that there is this relationship that follows the power law between the total amount of data and overall generalization error. And this is really important in a sense, because this is not something that we had with other machine learning algorithms. What this seems to be promising is a tool that can theoretically solve any problem to arbitrary accuracy, obviously within reason, if it is exposed to enough data. This is groundbreaking, and this is the real reason why we're seeing such a big progress in artificial intelligence right now, because this makes historically unsolvable problems, like a lot of problems in computer vision, quite easy, and it makes a lot of seemingly impossible problems, like, for example, self-driving car, which seemed impossible 2 decades ago, doable, expensive, but doable. But as always in life, nothing is for free. And there is a hidden trap in this diagram. And this hidden trap is hidden within those 3 letters here, this logarithmic scale. As I mentioned, it's a power law relationship. As a consequence, if you want to build some early prototype that achieves, say, 80% of accuracy, so you need to be, say, here. This is trivial because you'll just get some data, you'll get 1, 2 GPUs, and it will largely, most likely work. But if you want to take that prototype and improve it from, say, 80% to, say, 90%, that means that you need to provide an order of magnitude more data. And if you then want to improve it from 90 to, say, 99%, you need to provide another order of magnitude more data. And this is really challenging because some problems, in fact, a lot of problems cannot operate just with 80, 90% accurate models. A lot of problems are safety critical, like self-driving car, for example. And in this case, error rates that are typically expected from those algorithms vary somewhere between 10 to the power of -6 and 10 to the power of -9. So that's accuracies of 99.999999999%. Moreover, they need to maintain those accuracies across countless of conditions. So in presence of bicycles, animals, hazards on the road, at night, during twilight, when the snow is falling, when the fog is surrounding the car. As a consequence, this leads to extremely large volumes of data. And collecting extremely large volumes of data in itself is not a challenge, because it's actually quite manageable to build a fleet of 10, 20, 30, 80 cars and just spread them across the globe and have them drive and collect data. What is really difficult is to label those data sets. So this curve is not just an abstract diagram. This is actually our own internal data collection history. And currently we are hiring 1.5 thousand people full-time labeling the self-driving car images. That is clearly not something that every project can afford. In fact, majority of projects cannot afford this type of scale out, which means that even though we have this promise for extremely large models, it's not easy to reapply them. And in some situations, it's just physically not possible to do it at this scale. So think about more complex problems. Whereas it is possible to find a random person from the street and get that person to label road signs, pavements, pedestrians, it's not possible to find 1.5 thousand radiologists, pathologists to do the same within those more advanced disciplines. And it's not only about applications that require extreme level of specialization, extreme level of knowledge, but even in a lot of simpler problems, like translation, you need a level of expertise to be able to do the labeling. And that is problematic, because this means that we would need to exponentially increase the data collection and labeling effort to be able to take advantage of those larger data sets. And that is what historically prevented us from really training at larger scales. The inability to build data sets that are large enough. But that has started to change. 2 years ago, we, and by we I mean the research community, have started to see unprecedented success in a range of approaches that historically has never worked, namely self and unsupervised learning. If you don't know what those approaches are, the idea is not to rely on human-generated labels, but instead try to take advantage of the knowledge which is embedded into the data itself to learn some basic fundamental structures of those data sets and build a model that is not necessarily solving any particular problem, but a model which has robust representation capability and can be reapplied to other problems at much, much lower cost. Effectively, what we're trying to do, we're trying to cheat this curve. Rather than creating a vast supervised data set to get us here, we're trying to create a vast unsupervised data set, use it to get us to this point, and then fine-tune it on a much smaller supervised data set to get us to where we need to be. This is a very old idea. Those ideas were formulated decades ago. They never historically worked. But we've started to see quite a lot of success applying those ideas to real problems across multiple disciplines. And it all started with natural language processing. Within natural language processing, people revisited an old idea of masked language modeling. And the idea is simple. Rather than trying to teach neural networks some supervised tasks, such as translation or named entity recognition, we download unsupervised corpus. So, for example, we download the entire content of Wikipedia. We remove individual words, and we ask the neural network to predict those individual words. Or we ask the neural network, given 2 sentences, to guess whether those 2 sentences are indeed close or far away from each other. That way, we're teaching the neural network something about the language. In other disciplines, similar approaches appeared and started to work. For example, contrastive learning is an approach where you download a huge volume of unlabeled images, and you provide always two different image patches to a neural network, but those two different patches can originate from either single image or from two different images. You heavily process those patches, and you ask the neural network to guess whether they in fact originated from the same or different image or not. Thirdly, another approach that is currently the main approach used to solve problems such as classification with the ImageNet dataset. You train a teacher neural network on a smaller supervised dataset, and you use that teacher neural network to label a dataset that you download from, say, the internet, and you use those new soft labels to train the student, which is more robust than the teacher across a wide range of problems. And finally, this year, we started to see huge success, and it's only the 13th of January, we started to see huge success of combining visual information from images with the textual information from the websites. So the idea is simple. You get the image, you get the text, and you, rather than trying to train neural network on any particular task, you're just trying to train it at predicting whether that text has a chance of occurring close to the image. And those approaches started to work. And why is it important? It's important because it allows us to manage the cost. Suddenly, we can create substantially larger data sets, and we can train at much, much larger scales. In fact, we don't even have to create those data sets because they already exist. So every one of you today can go online and download a huge, huge textual data set. Every one of you can just go to the Wikipedia portal and download the entire English Wikipedia, or entire French Wikipedia, or entire German Wikipedia. Everyone can go online and download a common crow corpus. Some of those corpora are extremely large. So open a super large almanac is 800 billion words. But this is not just something specific to natural language processing. This is also something that you'll find in every single discipline. So you can download 8 billion videos from a data set called YouTube 8 million videos. Or you can download 1.1 million sporting videos, or 100 million hours of how-to videos. So computer vision and other unsupervised data sets are abundant. And this ability to take advantage of those unsupervised data sets allowed us to revisit the scaling clause that I've mentioned earlier. So it allowed us to see whether they work or whether they continue to work when we dramatically increase the size of our data set. And the answer to the question whether they work is definitely yes. So as we continue to grow natural language processing data sets, they continue to improve. Not only predictably, but almost like clockwork. Yes. If we continue to increase computer vision data sets, they continue to improve. And again, they continue to improve like clockwork. They improve more. They improve more for larger models. So as you increase the dataset size, it seems that it's necessary to increase model size, both in natural language processing and also in computer vision. Notice that smaller datasets like ResNet 50 are unable to cope with larger datasets. They not only do not improve, but they deteriorate. And this is not only something specific to ResNet 50, but even neural networks like ResNet 101 seem to be too small to cope with substantially larger datasets. So this is something you need to increase in tandem, and there is much more research needed and full understanding of how you need to increase it. But it also, we see this recurring pattern also in other disciplines. For example, exactly the same patterns are appearing when dealing with recommender systems. In this case, all of those models are plateauing because in recommender systems, you typically use very small models with respect to the dataset size. So as you increase the dataset size, they tend to plateau. But for larger models like BERT for rec, we can see that this line is straight. And it's more than just accuracy. those larger models are easier to design. This is a quote from a paper called Scaling Laws for Neural Language Models. We find that the precise architectural hyperparameters are unimportant compared to the overall scale of the language model. So as you make those models bigger, it becomes less important how exactly they are designed. Secondly, counterintuitively, they can be cheaper to train. They are cheaper to train because they tend to be dramatically more sample efficient. So here you see comparison of 4 different models. The blue line is 350 million parameters. The green line is 8 billion parameters. And you can see that the 8 billion parameter large model within just one epoch achieves accuracy, in this case, validation perplexity, that the smaller of the models cannot reach at all, despite the fact that it was exposed to 20 epochs of data. And again, this is something that we are seeing across multiple different disciplines. The larger the model gets, the more over-parameterized it is, the more sample efficient it gets, not only during initial pre-training, but also it generates higher quality features. So again, you can see comparison of 3 different models of 3 different orders of magnitude in terms of size and their ability to zero-shot, one-shot, and few-shot learn. You can see that the bigger the model gets, the more robust it gets and the more capable of few-shot learning it becomes. Once again, this is one-shot learning case. So the 175 billion parameter model within just single example, it becomes far, far better than the smaller counterparts when exposed to hundreds of examples. And again, this is not only something specific to NLP, this is something that we see almost identical curves in computer vision. Yes, and many other more disciplines. And the features generated by those large-scale and semi-supervised models are typically superior in almost any way from the features generated from supervised models, not only in a sense that they provide better end results measured in accuracy or whatever you use, but they also are more robust. They are more robust to the data shift, and they are more robust to the overall problem shift. So what you're seeing here is a comparison of performance of a neural network trained on ImageNet across multiple different image classification problems with the data substantially different from the original ImageNet dataset. And here is a comparison of a very large semi-self-supervised model. You can see that they do not deteriorate, despite the fact that the data distribution now is dramatically different. So they produce superior, more robust features. Okay, so that's it in terms of motivation. So what I wanted to show you in this segment is that large models and large data sets, at least with the current state of knowledge, seem unavoidable. So unless something fundamentally changes in our understanding of how to build at least natural perception models, so speech, language, computer vision models, this is the direction that we will be seeing across the next couple of years. Those models will not only increase slightly, they will increase by at least another 1, 2, maybe even 3 orders of magnitude, if not more. As a consequence, it becomes important to know how to train them. And there are 2 main concepts that you need to know about. In this little tutorial, we'll focus predominantly on the data parallel training approach. We can talk about model parallelism on another occasion if you're interested. But in essence, data parallelism addresses the problem of time. It allows you to train faster, whereas model parallelism addresses the problem of space, memory. It allows you to train bigger models. So as long as you can fit a neural network and a single example in a single GPU, you potentially do not need the model parallel approaches. And this is a vast majority of models that are still being used today. The idea of data parallelism is simple. If you don't know, I'll quickly recap. Every GPU gets a full copy of the neural network. Every GPU gets the same copy of the neural network, but every GPU gets a different random sample of the data. they both do the forward pass. As a consequence, they get a different output because they use different sample of the data. They both calculate loss, and as a consequence, they calculate different loss since they've got different samples of the data. They both calculate partial derivatives of loss with respect to weights, and then they consolidate that by averaging them. And they use the average gradient to make an update. This allows you to have more accurate estimation of the true gradient of the loss function with respect to weights. And as a consequence, this allows you to make larger steps. So this allows you to increase the learning rate and hopefully converge faster. I'll recap that once again, so don't worry if that wasn't clear. Model parallelism, on the other hand, is just an approach where you split the neural network across multiple GPUs. So rather than having an entire neural network on just one GPU, you have them, so you have half of it, say, on one GPU and half of it on another, and there are no strict rules on how to split them across multiple GPUs. They all get the same data sample. So those approaches are typically mixed. So in situations where you need model parallelism, you typically mix it with data parallelism. Okay, but let's focus now on data parallel training. Data parallel training, despite being quite easy, because what? You just provide different samples to different GPUs and then you average the gradients, is surprisingly complex to implement. And it's complex to implement because it pushes all of the technologies to the limit. So where with a single GPU case, you had to just deliver one batch of data. When you have two GPUs, you have to read from the disk 2 batches of data. So if one GPU trained at, say, 1,000 images per second, suddenly your storage technology needs to train at 2,000 images per second. Similarly, you need to deliver that data to the host that is doing the processing. You need to pre-process that data, so do some, say, augmentation, data cleaning. You need to cache 2 times more data. You have to deliver 2 times more data to the GPU. You have to do 2 times more compute on 2 different GPUs. You have to compute 2 different losses, and then you need to do additional communication. In order to average those gradients, you need to find a way of exchanging that gradient information between the GPUs. And this is non-trivial. If you think about even a simple neural network like ResNet-50, it can easily do several batches per second. As a consequence, this full gradient information needs to be exchanged across all GPUs participating in the training process several times a second. And ResNet-50 is a large model. It easily will consume, the gradients alone will easily consume 130, 150 megabytes. So every second you're exchanging gigabytes upon gigabytes of information between those GPUs, and any inefficiency in the implementation across any of those steps will lead to you not being able to fully utilize your GPU, and as a consequence, not scaling linearly. Once you've exchanged the gradients, the rest is quite simple. It ceases to be simple as the number of GPUs grows to very large values, but that's a secondary consideration. But it is from that point on simple. You use optimization algorithm of your choice to then update the weights across all of the GPUs. But that's a standard part of the process. Okay, so suddenly we didn't do much logically. We just averaged a bunch of gradients, but we've introduced a lot of challenges. So we've substantially amplified the infrastructure requirements. We have totally changed the way the code is implemented, because suddenly we need to do additional communication. And we need to coordinate execution between different GPUs, different machines. And we have also dramatically changed the algorithmic setting, because as we increase the batch size, our optimization process changes dramatically. Fortunately, in majority of cases, you don't really have to implement any of those from scratch. Instead, you will use different utilities, frameworks that will help you hide the complexity of that implementation. In today's talk, we'll talk about predominantly Horovod, or at least I'll mention Horovod very briefly. The reason why I'm mentioning Horovod is not because it's unique in any particular way. In fact, literally all of the deep learning frameworks implement the underlying logic in an identical way. In fact, they use the same underlying library. They all use NVIDIA Nickel library for implementing the communication. The reason why I'm talking about Horovod today is because we have proven that it works at very large scales. So the largest training jobs that we have executed using Horovod spawned across 27,000 GPUs and scaled perfectly linearly. Those were computer vision, image segmentation, and neural networks, namely Tiramisu and DeepLab v3. So with that introduction, let's dive into how to actually use Horovod for the training process and what Horovod is. Horovod is a utility that was born out of Uber Labs to address a wide range of their training challenges. A lot of it was driven around their effort focusing on training perception algorithms for self-driving cars. Horovod is effectively a library for distributed deep learning. It is not deep learning framework specific. In fact, it works with TensorFlow, Keras, PyTorch, MXNet, and there are some other experimental implementations as well. It's quite easy to deploy. You can install it with pip. And it hides the complexity of building what I just outlined to you earlier. It hides the need to use quite advanced algorithms for gradient exchange, gradient compression, and it leverages very high performance networking utilities and can take advantage of protocols such as remote direct memory access or GPU direct, which allow GPUs to exchange memory directly without involving the CPU in the process, even if those GPUs are on different servers in the network. With Horovod, infrastructure team can focus on their own work, so they can focus on providing the infrastructure needed for training, and machine learning engineers can use the deep learning frameworks of their choice. And those teams do not have to interact as much because Horovod isolates those concerns. It is also designed with simplicity in mind. And I will go through some examples of how to use Horovod in a second. So using Horovod was designed to make this deliberately as easy of a process as possible. So when you start to use Horovod for the first time, you need to start from somewhere. And typically, you would start with a piece of code that was implemented on just a single GPU. So you start with a neural network that works on a single GPU. You take that code and you do some modifications to that code to make it work on several GPUs. Let's go through some of those modifications. So obviously, like with every Python program, you have to import Horovod. In this case, it's a TensorFlow example, but in PyTorch it's identical. You need to initialize Horovod. Once you do that, you have to tell TensorFlow or PyTorch or MXNet that you're going to use just one GPU per process. This is important because your original code was designed to use just one GPU. So Horovod, rather than trying to force you to reorganize all of that code, it will spawn multiple copies of your original code across multiple GPUs and just coordinate communication between them. So by doing this, by writing those two lines, what you're saying is that if I need 4 GPUs, I will spawn 4 different processes, so 4 different copies of your program. And the first copy of your code, so copy 0, will get only GPU 0. The second copy of your code will get GPU 1, and so on. Those two lines make sure that every separate process gets exactly one copy of your code. You wrap. Once you do that, you take whatever neural network you have implemented with whatever optimizer you have selected, and you wrap it within a distributed optimizer. You make sure that your neural networks, so the copies between the GPUs, are always the same. Yes, you want to initialize them randomly, but you want all of the copies across all of the GPUs to be exactly the same. And those two lines of code, or those two lines, depending what is your implementation, will do just that. And then you do a bit of housekeeping. You make sure that you log and write to standard output only from one process at a time, because suddenly now, if you have 4, 5, 6, 8 copies of your program, you don't want every one of those copies to write to your screen. You do not want every one of those copies to write checkpoints. You just want one of those processes to write that information, and typically that's process 0, but it doesn't have to be. You can choose whichever process you want to do that. You need to then decide how are you going to split the data between the workers. So if you had just one process, it was obvious. That process had to process all of the data. But suddenly, if we have now 2 workers, we need to choose how are we going to sample the original data set. One of the most robust approaches is to take that data and at the beginning of every epoch, shuffle that data randomly and ask worker 1 to process just the first half of the data, and ask worker 2 to process the second half of the data. This is statistically correct, but this requires writing additional code to actually implement that shuffle and make sure that those workers do not overlap in terms of their data access. Therefore, in a lot of problems, people don't bother, and they just allow the workers to randomly sample from the entire data set, accepting the fact that there will be some duplications. This is not statistically correct, but for majority of large data sets, it works just fine. And it is much, much easier to implement. And in fact, this shuffle operator is not even technically needed, since those workers are sampling at random. And that's it. We have now migrated our code from single GPU to multi-GPU implementation. Let's look at all of that from the beginning. So let's look at it on the one page. So we have our existing neural network, which was importing TensorFlow or PyTorch. It doesn't matter, the syntax is identical. We need to now import Horovod. We need to initialize Horovod. We need to point every worker to a single GPU. Obviously, we want to train faster. So with whatever optimizer we have selected, we have to scale the learning rate accordingly. We have to wrap our optimizer of choice into Horovod distributed optimizer. We have to execute the synchronization between the models, make sure that we are just checkpointing on one process, and that's it. Suddenly, this code is capable of executing across multiple GPUs, in fact, across multiple servers. The process is identical across all of the deep learning frameworks. The only difference is that you import a different variant of Horovod, and there are some minor syntactic changes. So if you use TensorFlow, you import horovod.tensorflow as Horovod. If you use Keras, you use horovod.keras. If you use TensorFlow Keras, you use Horovod TensorFlow Keras. If you use Torch, you import Horovod Torch. If you use MXNet, MXNet, and there are some other experimental implementations as well. Okay, so we've made those modifications, but what now? Do I just run that code as is and it will just work? So the answer is no. You need to actually point those processes to appropriate GPUs. You can point them using many different approaches. The standard one that we use and we distribute with our TensorFlow container is by using MPI. And Horovod actually hides the MPI between this Horovod run script. So if you now want to execute your code on 4 GPUs on a single machine, on a single computer. You then have to say horovod run. NP stands for number of processes, in this case 4. Since we are assigning a single GPU to a single process, this also means I would like 4 GPUs, please. And then we just pass our code. That's it. This will run our code on 4 GPUs. If we now want to say train on 16 GPUs, we need to do the same. We need to do horovod run. We need to say, I would like 16 GPUs, please. But I would like 4 GPUs on server 1, and this is the address of that server 1, 4 GPUs at server 2, 4 GPUs at server 3, 4 GPUs at server 4, and here is my code. And that's theoretically it. Obviously, you need to set up authentication in a way that those servers actually respond to your request. That is typically something that is done by the infrastructure team. Beyond that, this will scale to, as I mentioned, 27,000 GPUs. Obviously, your mileage will vary. Admittedly, Deep Lab v3 and Tiramisu are very large neural networks. And it's easier to scale large neural networks linearly than it is to scale small neural networks, because large neural networks spend more time processing a single sample. They spend more time calculating between the communication. So it's slightly easier, but nevertheless, with this, you can scale to very, very large systems. If you're one of those people that would like to know what's inside that horovod run script, there is actually no magic. Behind the scenes, it just executes, for those of you with HPC background, an MPI run command and sets up some of the key parameters to the default values. So in fact, this horovod run is just a one-liner shell script. It doesn't do much substantially more than that, but just wrap it in a MPI run statement. Horovod doesn't have to be executed with NPI. It can also be orchestrated via other orchestration engines. For example, it comes with a Spark integration. So if you're not using MPI in your organization, don't worry. It also can be executed in many, many different ways. There are at least 4 or 5 different execution engines, execution mechanisms, however you want to call them, that you can do to execute just this. But in academic setting, in scientific setting, this is by far the most frequent route. Okay, so what did we learn? We learned why would we be bothered? That's one thing. We've identified theoretically how to do it. We've seen the code that is required to implement that multi-GPU training, but now there are some outstanding questions that we should be asking ourselves. First of all, can we increase the batch size indefinitely? So I've alluded to the fact that you can, and if you measure the scalability in terms of images per second, queries per second, sequences per second, then the answer is definitely yes. You can scale to as big of a system as you want, and this metric, so images per second, sequences per second, will scale linearly. But it doesn't matter in a way, because it doesn't mean that you will be able to reduce the training time, because you don't care about images per second. What you really care about is how many minutes, hours, days does it take for the neural network to converge. And to answer that question, it's much, much more difficult. And it turns out, and again, the theory of this is not fully understood, that there is this regime of scaling, which seems to be specific to the complexity of the dataset. Whereas there is this point, this critical batch size, up to which you scale almost perfectly. So you start with a batch, say, of 10, and it took, say, an hour to train. You increase the batch size to 20, and it takes half an hour to train. You increase the batch size to 40, and it takes 15 minutes to train. So up to that critical batch size, the scaling is almost like clockwork. It's almost perfectly linear, obviously, if you manage to get rid of all of the bottlenecks in your code. But there is no straightforward way of establishing where that critical batch size is. And that critical batch size seems to be a function of the data complexity. And once you pass that critical batch size, you continue to speed up as you add more GPUs, but you by no means can match it. So there is this point where you have, say, 100 GPUs, and you move from 100 GPUs to 200 GPUs, but your training time doesn't half, but maybe reduces only by 20%. And what you're seeing here are results obtained experimentally. And I am not aware of any very good method of finding where that batch is. I just know a heuristic that I'll share with you. That heuristic was described by OpenAI, and it suggests that critical batch size can be estimated by calculating this so-called gradient noise scale. And this gradient noise scale, effectively, let me read it out loud, measures the variation of the gradients between different training examples. So effectively, you train your neural network, you pass the data through the neural network as is, all of it, and you look at the total variation that you had between different gradients. The bigger that variation is, the bigger the critical batch size will be. This is some form of a proxy to how complex the data set is. The bigger, more versatile, more varied the data set is, the bigger that critical batch size is. With all of that, let me maybe translate all of this into something that is easier to consume. In practice, this is not something that majority of you will have to care. So I'm not sure whether you're aware of the ML-Perf competition. It's just an event where there is this independent organization that is trying to evaluate the performance of training and inference systems. And we've been submitting to this competition across all of the different tasks. So I'm showing that to demonstrate the levels at which still you obtain linear scaling. So if we look at language translation, so translation from, say, German to English with non-recurrent neural networks, so with transformers, we've managed to scale linearly to 480 GPUs. And most likely we would scale further. It's just that at this point, with this benchmark, the training time drops below a minute. We've managed to scale translation with recurrent neural network with Google Neural Machine Translation Model to 1,024 GPUs. And again, most likely we would be able to scale it further down. But again, at this point of time, it's below a minute, the training time. So there's no sense to further scale it up. We've managed to train ResNet 50 on 1,800 GPUs. Again, below a minute. So further scaling doesn't add any value whatsoever. We've managed to scale a single shot detector. I don't remember what was the backbone. Again, 1,000 GPUs. Again, training time below a minute. Training of BERT to 2,000 GPUs. This is BERT large. Again, below a minute. A deep learning recommendation model. This is 8 GPUs, but those tip models tend to be quite small. That's why it's just 3 minutes. It didn't make much sense to scale further. Mask RCNN on 250 GPUs to 10 minutes. Minigo Go on 1,800 GPUs to 17 minutes. So the reason why I'm showing you this is that in practical terms, you will it is unlikely that you will have to care about this critical batch size. For all intents and purposes, if you're using a non-trivial data set, so not MNIST, not CFAR, but even something slightly larger like ImageNet, the fact that this critical batch size exists will not matter to you because it will be at the beyond your reach. Not many people in the world have a privilege to train on 2,000 GPUs, 10,000 GPUs at a time. So for all intents and purposes, yes, you can scale to as many GPUs as you want. It doesn't mean that it's trivial. So there are some other phenomena that you have to be cautious about. So as you increase the batch size, what happens is that you observe degradation in model performance. This degradation in model performance is predominantly seen in the validation error, not in the training error. That is why people refer to it as a validation, as a generalization gap problem. It turns out that if you take a code that works well on a small batch, in this case ResNet 50, trained on 256, batch 256, it converges just fine. But if you don't do anything, and if you just naively increase the batch size, what happens is that you observe a fairly dramatic degradation in model performance. So your model, yes, converges maybe, but it doesn't converge like here to 71, 72%, but say converges to 68 at batch 16K, or to 58 or 55 at batch 32K. And I just want to point out that batch of 16K is not a huge batch. Now Ampere, so the latest generation of GPUs, the latest SKU has 80 gigabytes of RAM. So this is, I think, roughly either 8, I think this is 8 GPUs. With 8 Ampere GPUs, you will already see a fairly dramatic degradation in performance. And with 16, it will be unacceptable. In this case, this is below AlexNet performance. Vanilla AlexNet. So that is why, like in 2017, 2018, people like Jan LeCun would say that friends don't allow friends to train with large batches. I think he's contributed with that. I'm not sure whether that's true.
Which Adam tries to translate in friends tell friends the recipes how to manage large batch training.
Exactly. But the thing is that that was the status quo in 2017, late 2017. A lot has changed since 2017. We've gained a lot of understanding of why do those neural networks fail. And we don't have time to go into the theoretical deliberations of why exactly does this happen, yet not to mention that no one really knows the full mathematics of why this exactly happens. We just have heuristics, we just have empirical observations of the optimization process. But what has happened since 2017, we've learned a lot how to tackle this problem. There are quite a few approaches. There are actually countless approaches, but the approach that we have used across all of the benchmarks that you've seen, they fall into just one category of approaches. In particular, we use 3 different mechanisms across all of those training jobs. First of all, we use warm-up strategy. Warm-up strategy, I don't have a slide on it, but it's trivial. You don't start with a large learning rate, but you start with a reasonably small learning rate. You increase the learning rate very quickly to allow the neural network to stabilize, and then you start decreasing it following your learning rate schedule. We use ghost batch normalization. Ghost batch normalization is just batch normalization carried out per GPU. So rather than obtaining mean and standard deviation for the entire batch across all of the GPUs, we calculated only for a single GPU. And this is the default implementation, by the way, across many deep learning frameworks. And that adds a level of noise to the calculation. But we use also not a derivative, one of many derivatives of the algorithm that is mentioned here. Lars stands for layer-wise, so hence L, adaptive rate scaling. Effectively, rather than having one global learning rate, we automatically adapt learning rates, and we have one learning rate per layer. And that learning rate magnitude is calculated in a very simplistic way. We take the total magnitude of the gradients and we divide it by total magnitude of the weights. So we prevent a situation where we make very, very, very large gradient updates, which are not proportional to the weights in a given layer. And that stabilizes the training considerably. Since LARS was first described in 2017, there were countless updates to it. LARS was enhanced with clipping, which further improves its stability and makes it less sensitive to hyperparameter change. And also, it was revisited by Google initially, who have created a variant called LAMB, because LARS and LARC were predominantly designed for stochastic gradient descent. They didn't work particularly well with Adam, and LAMB is a variant that can work with Adam quite robustly, and it does. And in fact, it is right now deeply integrated into every single transformer neural network that I know of. I don't think anyone is training transformers without LAMB, irrespectively of our size. You just never pay attention when you look at the code. It's somewhere there. It's just one line code. And even LAMB now undergone several iterations, and we have much more robust and much more performant implementation called ND-LAMB, which aggregates all of the learning that we had from training these models at this large scale. It's trivial to use. It's literally one line of code that you need to add. Please use it even if you don't train on very large systems. It helps with convergence, and it helps with training stability. In a nutshell, you can train with very, very large batch sizes, to the extent where even on smaller systems, so even if we don't have thousands of GPUs and CPUs, we'll pretend as if we have. So frequently, a lot of the code that we release will do gradient aggregation. So they will do forward pass, backward pass, get the gradient, and not do the gradient update, instead do another forward pass, backward pass, average those two, do another forward pass, backward pass, do it a couple of times, aggregate, and only then do one larger update. This is, in many cases, much more stable and quicker approach than just doing noisy gradient updates. We have also, since then, noticed that even though Adam plus LAMB, Adam plus LARC, yes, it's possible to integrate those as well, works well for a lot of problems, there are some inherent problems, predominantly revolving around how Adam is designed. Adam has a lot of problems, optimizer. One of the biggest ones is the fact that it is just not very good at managing memory. So the overheads of using Adam are actually quite substantial. So for every parameter, if you train in FP16, you'll store 12 bytes of additional information for Adam states and such. Therefore, we have created a new algorithm that is extremely promising. It's not as widely used as LAMB, by no means, but it generates better results than Adam plus LAMB, Adam plus LARC, and it consumes much less memory. That algorithm is called Novograd. Effectively, it is very similar in its implementation to Adam, but maintains the momentum information per layer and not per weight. So those moving averages are calculated on a per layer basis. That's it. With those key techniques, you will be able to scale to fairly large batches. And if you're working on a problem that is being deployed on very large systems, and if your batch size is growing to a larger size, do reach out. We'll be very happy to help you. So you'll find my contact details if you haven't already seen them later on as well. Okay, so on data parallelism front, that's more or less everything that I had. I wanted to wrap up by mentioning model parallelism because it's becoming more and more important right now. I will not spend too much time on it, but I wanted to spend some time on it. And how much time do we have left?
Yeah,
could you remind me?
Almost a bit more, 34 minutes left to be
outstanding. So quite
Adam,
easily. So
Adam,
no problem. Yes.
If you don't mind, I would share a few experiences. So for the audience, Adam taught me how to do it, so the most I know about this topic, I know it from Adam, and so I was looking at it from a practical point of view, and one of the biggest things which were outlined before was this whole thing is easy and useful. Also, because many of us develop on a desktop, but then they send their code later to a big system, and this is something which is perfectly addressed, right? You have a single process paradigm, and then when necessary, you go on a big system with multiple processes, multiple GPUs, or even more. So that's a perfect fit for working on a desktop and then looking and working on a cluster. It also is one of the very big arguments for those who operate the IT, because they can standardize the IT. You can standardize a lot. You can standardize your code, and it's kind of a rubber band. So it's our customers basically say they treat this as a de facto standard of doing multi-GPU compute. Then on the journey of convergence, which Adam pointed out, actually you can experience a lot of the convergence behavior. And once was one of my first experiments. Take a simple problem, for example, an MNIST, which you almost can solve with a pencil, but here you can experience the deterioration of the convergence very easily. That's an easy problem to scale the batch size in crazy dimensions. So that's a nice example to find it out. And the other recipes, because I help a lot of customers in going that path. They come from a single GPU code base and want to use more resources to innovate quicker. And then this is basically the default setting. And so the transformation recipes Adam has given are the starting base. They work in many cases. And then I basically say, okay, let's start gradually. And let's try 1 GPU, let's try 4, and also observe how the parameter space is shifting a little bit. As another best practice there, I deploy a little bit of parameter search to look a little bit left and right my parameter corridor. And so this is a few basic recipes or behavior I took over time to learn how to estimate the right hyperparameter set when the batch size is getting bigger. So that helped me a lot.
That's something that we'll dive in tomorrow. Yes, that's correct.
Yes.
Yes and no. Okay.
No, yes and no, because I the meeting did not show up in the calendar. I must have some problem on my end. Yes, let's go on that tomorrow.
Sure.
Yeah.
But yeah, Adolf is perfectly right. So when our latest ML performance result for BERT came up, I was actually quite shocked because they've managed to train it on 8 GPUs in 49 minutes. And I was scratching my head quite a bit. How how the hell did they do that? Because I know that Ampere is quicker, but on previous benchmark on 8-volt GPUs, it took like 153 hours. It's not that much quicker. It's definitely not like 200 times quicker than Volta. It is quicker, but not by that much. So I've looked into the code here, and yes, free 4x was because of the GPU acceleration. Additional free 4x was because of the better quality of code. So they did something that is called fusing kernels in the multi-head attention. So they actually wrote better quality implementation of it. But the rest of it, it was just a very robust hyperparameter search. Majority of that speed up actually comes from finding hyperparameters that made sense. Yes.
Yeah, hi, Adam and Adolf. Just a quick comment to everyone. Firstly, I think it is my mistake to not send the calendar invitations.
That's okay.
We write back and forth, but I didn't send the calendar invitation, so things messed up a bit. But thanks for being here.
We will cover it. Don't worry.
Yeah. And it is great that you can still deliver, even though you think it is 1 week earlier than.
I was prepared way in advance. I hate preparing on the last moment.
Yeah.
That's always very hurtful. By the way, we haven't finished.
We have about 28 minutes left, but I think let's give the audience about 10 minutes in the end to ask questions.
Yeah, sure.
And
I have about 10 minutes of content more.
Yeah, okay.
At least.
Yeah, perfect. Thank you.
And so I think we can have the first round of questions right now if you want, and then because the rest of it is just an observation that it's not only about data parallelism. So we're going slightly off tangent right now, but I think it's an important topic. Any questions so far? Anything you would like guys to discuss about data parallelism?
Yes, I think that's a good idea. It's before we move to the next part.
Sure.
Yeah. So if you would like to ask a question, just type something in the chat box. So we
in the chat. Let me open the chat as well.
Like you take the cue, and then you can turn on the microphone and ask directly. Otherwise, you can type the question in the chat box. It also works.
Let's quickly look where the chat is. Oh, there is 25 things in the chat right now, but a lot of them are because of the fact that we haven't started. I guess anything related to the content itself? Not really.
Well, from my end, I haven't seen any questions.
Okay.
Yeah. And yeah, all the previously are the practical questions. So
sure.
To everyone, if you have.
Yeah, I monitor the chat, and Adam, you can go ahead. I monitor the chat during that time.
That's great.
Yep. Yeah. Okay, so we've talked about. Go on.
There's the first question. Yeah, please, Adolf, please, you take the chat and push the question to Adam.
So what's the question? Could you read it out loud?
No, I do it in parallel. If you want to go on, I do it in parallel and type.
All right. So then I read the first questions. Does it work with AMD? That's a question from Christian.
Horovod? Yes, Horovod will not care. So the only thing, Horovod doesn't know what the GPU it's executing on. You will have to disable Nickel as a communication library, but it will work just fine. Yeah. Obviously, you need to find the implementation of the deep learning framework that will actually work with AMD and write the code in a way that will work. But sure, yeah, no problem whatsoever. I don't know. We don't test on AMD, so I don't know how well it will work. But
well, but you said it conceptually. There's nothing which is in the way from an implementation perspective. It is very important that the communication is going very quick, and the the implementation, what we use is exactly doing this, because the moment communication takes a bigger part than the compute, then the whole equation is going to fail. The scale is getting very worse. So it is critical for the implementation. There is more on it on the in the other deck.
Yep. The only thing Horovod does really is it takes gradients across all of the processes and it tries to average them, and it tries to do it very well. Yes, and doing it very well is difficult, but it has nothing. It has beyond the fact that it's built on top of nickel, which you will have to turn off, because nickel is an NVIDIA library that allows individual GPUs to talk to each other. It will work just fine. It's just it will have to fall back on TCP/IP and do a round trip across the CPU, unless there is something from AMD that they provide. But again, that's not something that we're testing. I know it works on a CPU just fine.
Yeah. There are just others coming in, and relationship of batch size and loss. So the loss approach is effective because it avoids it ensures conversions by choosing the right kind of per layer learning rate. So the observation which the colleagues made, which triggered them to build LAS, was during the training, they experienced that instability on certain layers. So this is what triggered the design, and to get it under control, they basically thought, let's leave the other rates kind of in place, but adjust it where it's necessary, and that's the mental model behind. So
yeah, and it makes sense, you know, if you have weights of, say, order of magnitude between 0 and 100, I don't know, I'm just making it up, and suddenly you want to make a gradient update of 10 million, you know, it might not be necessarily the best idea. So doing it like that just logically makes sense.
I think there is one question previous to that one. It's say in the slide about critical batch size, looking at the plots, does x-axis describe the total number of example across all GPUs?
So this is the total batch size. By total batch size, I mean across all GPUs. That's correct. So, yeah. In fact, this study doesn't care about whether it's training on a GPU, CPU. In fact, I think this study was carried out on a very small system. They were just aggregating the batch in memory. Yes.
So we treat basically a multi-GPU system has a per GPU batch, but the batch size we're talking about here is basically the amount of workers multiplied by the per GPU per worker batch, which is the overall batch size on the x-axis.
An amount of samples that you will use for a gradient update. Okay. Anything else, or shall I crack on?
I think you can crack on. You will touch does Horovod support model parallelism as well? I can imagine. This is a question in the chat. So the answer is yes. And,
So is it only about data parallelism? Yeah, for a lot of you, yes. Yeah, so for a lot of you, that's it. You just want to get your model to train faster. But what we are starting to see is that across many, many disciplines, we're at a point where the models are getting big. Not only the data sets, you know, when the data set gets big, that's one problem. It takes longer to train, but when the model gets bigger, suddenly it's becoming difficult to store it into the memory. And a lot of you might have seen graphs that look like this, which I don't find very informative. They don't help us understand how big those models are starting to become. So what I did, I literally translated this graph into slightly different representation that I think makes more sense. So I want to share with you just how big those models are starting to become. So if you try to compare ResNet 50, which is a medium-sized computer vision neural network, to what was a year ago perceived as a very large a model for natural language processing, yes, BERT large is bigger than ResNet 50. It is not dramatically bigger, it is bigger, yes. But what we've seen in 2020 is unprecedented. Namely, we've started to see neural networks that are so vast that in comparison, ResNet 50 disappears. So you shouldn't be able to see the dot representing ResNet 50. And unless you have a very decent network connection and your video is not compressed, you should also not be able to see BERT large in comparison. And yes, I know models like this are still a bit of science fiction for a lot of you, but we start to see models like Megatron 8 billion, Megatron 1 billion used very, very regularly in medical natural language processing, for example, with huge success. And the reason for that is that those models, they just behave better. And the same is not just specific to natural language processing. In computer vision, it is becoming more and more apparent that in order to make further progress, we will need to combine language with images. And this is, in fact, what is happening, and state-of-the-art models all do that right now. Hopefully, we will have more clarity in the near future. So as a consequence, a lot of those models, in fact, at around this point, your model gets so big that it won't fit into a GPU. In fact, this model is so big, if you just take a single GPU and you would hypothetically fit that model in, it would take you about 31 years to train. So let's look on, what are the boundaries? At which point you really need to start thinking about model parallelism. And I don't have an example for every conceivable neural network, but let's think abstractly. Let's think about a model with 1 billion parameters, trained using mixed precision, so FP16, and trained with Adam optimizer. So for 1 billion parameters, we need 10 to the power of 9 numbers. Each one of those numbers is FP16, so it's 2 bytes per parameter. We also need additional 2 bytes per gradient, and we need additional 12 bytes for Adam optimizer states. So overall, we need 10 to the power of 9 times 16 bytes, 14 gigabytes of memory, just to store parameter and optimizer states. But what about activations? What about 2 to 3 billion parameter models? They are not fitting into the GPU. In fact, if you use a GPU that has a network that has 1.3 billion parameters, in this case, transformer neural network, it's not fitting into 32 gigs of memory. It's just not. That is why it's becoming more and more important to also know how to effectively implement model parallel models. In some disciplines, it's easier than in others. In fact, in language modeling, we have a very robust implementation of transformer called Megatron, which is nothing but a model parallel, efficiently implemented multi-layered perceptron and self-attention. And this implementation scales linearly in both model and data parallel regime on a single node and across multiple servers. But this is not necessarily the end of the story, because this effort, replicating this effort across countless different neural network architectures, is not something that community will be able to do robustly. That's why we started to see a new wave of progress in deep learning utilities. Utilities such as mesh TensorFlow are emerging. In particular, the tool that I'm particularly excited about is this utility written predominantly by Microsoft, yet we have collaborated with them to some extent on it, called DeepSpeed. I'm not going to go into a huge amount of detail about it, but I just want to mention it because it already is playing a massive role in the progress that we are seeing. Effectively, the idea is simple. When you train in a data parallel way, we've discussed it. Every GPU stores the same copy of the neural network. Every GPU stores the same copy of the gradient optimizer states. And that is instinctively redundant. So what DeepSpeed and Microsoft Zero are trying to do is not to do it, to exchange memory for additional communication, which because of the networks such as NVLink, I'm not sure you've heard about it, but modern GPUs can talk to each other at huge speeds because of a bus called NVLink that interconnects them in some systems. You can trade off this memory into communication. And since this communication can be done asynchronously, so this is not a sequential process necessarily, it does not create any latency. As a consequence, you can fit dramatically larger models. They estimated that models of 200 billion should be feasible, and they are working towards additional changes that are going to bring it closer to 1 trillion. In fact, I can tell you for a fact that 200 billion parameters models are possible because we're working on them. It executes 10 times faster than comparable implementation, and it's actually very easy to use. It's in terms of complexity of use, it's similar to what Horovod offers. And it offers you this very robust set of utilities to reduce the memory consumption. It not only comes with this zero implementation of data parallel training, but with a broad range of other utilities, such as gradient checkpointing, many more that we don't have time for today. One of the final things that I would like to point out, and this will be a bit of a marketing pitch, if you wish, is that software quality matters. Yeah. Believe it or not. It makes it, yes?
Excuse me, before you go further, previously there is a question on the
sure.
graph. Please go back 2 slides, I think.
Sorry, wrong way. This one?
Yeah.
The previous one?
Yeah, there's a question in the chat. No, the previous. Go to next one.
The relationship of the size of the model.
No, this.
I cannot see the chat and see the slides at the same time. So give me a second.
88, slide 88, I think.
Here we go. No problem.
Ask, or I don't know which slide he really this graph.
Adam, you explained the growth of the models to motivate the size.
Yep, this one.
This does not fit, right? On the x-axis, the model grows, and the y-axis was.
Oh, they represent nothing. So the only thing that matters here is the size of the bubble. The size of the bubble represents the total number of parameters. And those are just different models. And I've arranged them in a way that is semi-chronological. So
does it answer
it's
the
just
question? 19? I'm sorry for the pronunciation. Yeah, and well, personally, I didn't catch the answer for Ting Wu question about does Hoverod support model parallelism?
Yes and no. Yes, it does, in a sense that you can, if you have, say, PyTorch or TensorFlow code, and if you tell that code not to pin a single process to a single GPU, but pin two GPUs to a single process, and if you use built-in PyTorch, TensorFlow, model parallel features, Horovod will gracefully communicate. So it will not make any redundant communication between unnecessary GPUs. So in a sense, yes, but it doesn't provide you with any tools to simplify the process of building those model parallel applications. So for simple model parallel training, yes, it does. For more complex stuff, it was never designed to do that. Whether it will evolve to do that, I don't know. What we're starting to see is other tools to do that, like this DeepSpeed +0 or Mesh TensorFlow.
Yeah.
Because it's a problem in itself. It's not obvious how to distribute your model across multiple GPUs. Do you put first 2 layers on one GPU, second 2 layers on another GPU? Not really, because then one of the GPUs will always be idle. Do you put a left-hand side of your model on one GPU, right-hand side of the model on the other? Not really, because you create huge amount of communication for activation exchange. So how do you distribute your model? Answering that question is non-trivial. And Horowitz will not help you in making those decisions. So yes, it supports it. If you design it, it will work, but it is not making your life easier in any way.
Thank you.
Okay, so
Next
we were
question,
saying that.
like to take, or we go further? About 10 minutes left.
Let's take another question. I just have like 3-4 slides left. It doesn't matter.
You mentioned gradient accumulation could be used to approximate large batch sizes. How does this work with batch normalization, often used in vision models?
Not to approximate, you get exactly the same results. And batch normalization, that's quite easy as well, because the only thing that batch normalization does, it calculates mean and some basic statistical properties. You can calculate them in a rolling way, in a rolling fashion, or you can just maintain all of those statistics in memory. That's fine. So that there is no problem whatsoever. In fact, in PyTorch it's trivial. You just maintain the gradients, you average them out, and only then do a gradient update. It's maybe it's 2-3 lines of code. In TensorFlow, it's slightly more involved.
Great.
Again, you get exactly the same results. It's you're not missing anything.
Yes. So
anything else?
Move ahead, I think.
Sure. So with that, I wanted to mention something that Adolf hinted upon earlier. Software quality makes a huge difference. So when you've been working with one GPU and one CPU, you had an entire disk at your disposal. You had an entire CPU at your disposal. The ratio between the GPU and all of the other system components was favorable for those other system components. Not to mention that in a desktop, you most likely don't have a latest and greatest GPU either. The moment you scale, all of those components get under huge amount of pressure. And building code that can keep up with the GPU is difficult. It is not only difficult for you, it is in fact difficult for us. That is why for the last almost 4 years now, since I think December 2016, we had a fairly large team, a couple hundred people devoted exclusively to making optimizations across the entire stack. So we have a team that is on a weekly call with MXNet, PyTorch, TensorFlow team that are optimizing the code of those deep learning libraries and all of the downstream code. And as a consequence, we publish updates to MXNet, PyTorch, TensorFlow, and countless other utilities on a monthly basis on a platform that we call NGC. NGC is free to use. It's available for you to use today. Just go to ngc.nvidia.com and download yourself a PyTorch TensorFlow container. You will find that the code that we distribute is quite robust. And what this graph shows you is the difference in training speed on ResNet 50 on exactly the same hardware at 4 different points of time, starting from August 2017 till December 2019. I should update this slide. You will see that with MXNet, for example, in August 2017, we could process about 5,500 images per second. And in December 19, almost 11,000 images per second. Similarly, in PyTorch, TensorFlow, software quality makes huge difference. And this is not a speed difference that you can throw to the bin. This means that you need twice as many GPUs if you use this quality of code. So please use NGC. You'll find all sorts of very useful assets there. Not only containers with TensorFlow and such, but a lot of trained models, correctly pre-trained models that you can fine-tune. You'll find model code. You'll use Helm charts for deploying of applications. You'll use inferencing tools. Use NGC it will save you a lot of hassle. This is how we've managed to do things such as reduce the training time of BERT to just 49 minutes. It requires huge amount of engineering effort. Tap into that effort. Don't try to rediscover the things that we have done. Build on that basis. Again, it's free of charge. For majority of stuff, you don't even have to create an account. And the final thing, when choosing systems for training your neural networks, it's important to mention that it's not just a lot of GPUs. Especially now that GPUs are getting so much faster, so much significantly faster than CPUs. So we're accelerating at a rate much higher than the single-threaded computing is accelerating. The load on the system as a consequence is increasing, and it's tremendously important to build balanced solutions. I will not recommend you any particular system, but just make sure that when you choose a system for training, you choose storage technology, so disks that actually have a chance of keeping up. So if you're training a neural network at, say, 11,000 images per second, and you buy a disk that can only deliver 8,000 images per second, you will unavoidably train at 8,000 images per second. Similarly, choose the CPU that can actually keep up with your data augmentation. Because if it cannot keep up, you will be bottlenecked by the CPU. Choose a system that has enough PCI Express architecture to be able to deliver data, checkpoints, and all of the information to and from the GPU, and make sure that the GPUs have enough networking to communicate together. Finally, if you're going to scale your training to more than one server, so say even just to 2 servers, the same applies to networking. You need to have enough networking to be able to exchange the gradients between the GPUs and not to bottleneck the GPU. If you skip any of those components, it will become a bottleneck and everything will be waiting for it. Preferably, you don't want that. You want the GPU to be the ultimate bottleneck. You want it to be operating at 99% utilization, not your disk or not your CPU. Will we need to run multi-node training jobs? I don't know. What I do know is that for a neural network like GPT-3, it would take about 4 years to train that model on 8 GPUs. So for some problem, yes. For some problem, no. A lot of people already realize that. So we've been working over the last 3 years to build, more than that, to build good quality data center architectures. They're not only designing individual systems, but building data center scale computers. We've been doing it in HPC for a while, but we've been really focusing on machine learning and artificial intelligence. And we built a reference design on top of which we built recently a Selene supercomputer, which is now the 5th of the top 500, not the 7th. And we are not alone. We have quite a few customers that are replicating that design in one form or another. Not every one of those customers is taking identical system and of identical scale, but we see more and more people just design this system as is, because not many people actually have tested systems like that. So it's the easiest route, if you wish. And the reason why they do it is because there is low-hanging fruit. So it's unquestionable that in the next 2 years, whomever will be able to master the biggest amount of compute will get the NIPS Best Paper Award, like it happened this year and the last year, actually. Because this low-hanging fruit is obvious. We know what we need to do in the next 2 years to further improve those models. And people will reach out for that low-hanging fruit. There's one more thing. We have this organization called NVIDIA AI Technology Center. And they have published a very, very good GitHub repository, including all of the utilities that you really should know about. So there are examples there of Horovod, there are examples there of DALI, there are examples there of other utilities. And they didn't just publish this GitLab utility and leave it as is, but they've recorded a series of YouTube videos describing how to use all of those different tools. This also includes tools for profiling neural network and then deploying them to production. I would highly recommend checking this toolkit out. Do reach out if you're working on larger scale training jobs. Check out the toolkit. Check out our DLI, hands-on DLI that we have on in our portal, to which I think you have access to, where you have codes for that will give you hands-on experience. And also check out the GTC talks that are focusing on large-scale training, and hopefully I'll see you on the next GTC, which is in April. And that's everything that I had to say. Now, just time for conversation, question, and we'll crack on tomorrow same time. Or actually, no, half an hour earlier.
Yeah, that's right. Thank you. Right on time to finish it. Thank you, Adam.
Yeah, I was rushing a bit to try to hit the timing.
Yeah. Thank you, everyone, for participating today. I will send out the Zoom information for tomorrow, and see you tomorrow. Thank you.
Thank you kindly.
Yeah. Yeah.
Have a good afternoon.
Yes, thanks
Afternoon, good
for
evening,
organizing, Wang.
good morning to everyone if you are somewhere.
Hello.
Yeah, okay.